Works? It works? Okay. Well, first of all, thanks for inviting me to come and speak today about my favorite topic, which is solving conic optimization problem. So once again, this talk will not be about polynomial optimization, but about solving second-order cone problems and semi-definite problems, which, as far as I understand, is an important tool when you're solving polynomial optimization problems. Okay, let me see, where do we have page down? So here's the outline of my talk. What is MOSEK? What kind of conic problems can MOSEK solve? What are the interfaces? What are the algorithms? I don't think I will say too much about that given the time limitation. Probably not much about the implementation either. A little bit benchmark results and then summary and conclusions. But the emphasis will be on the first part. Okay, so MOSEK is a software package for large-scale optimization problems, and version 1 was released in '99, and the latest version 7 was released in 2013 here in May. And we do linear and conic quadratic plus a mixed integer variable. And conic quadratic is the same as second order cone. So some say Lorentz cone, some say the second order cone, some say the quadratic cone, and I prefer the quadratic cone. But this is the same. And we do these things even in the mixed integer case, and there are some preliminary results at Middleman's website that for the few problems that he tested, we are doing quite well on mixed integer conic quadratic problems. In the latest version 7, we add semi-definite optimization, and that's what I'm going to talk about today. We have interfaces for C, Java, .NET, and Python, and there's also interfaces to MOSEK from the modeling languages, AMPL, AIMS, GAMS. You can use it from MATLAB and R. Not all features is available in all modeling languages. For instance, you cannot use the semi-definite stuff from any of AMPL or AIMS or GAMS. Okay. MOSEK, I quite frequently ask, so how much money do we have to pay if we are academic? It's completely free to use for academics. Just go to our website. Don't send me an email. Go to our website and read the website. Okay, it's as simple as that. If you send me an email, maybe I'm on vacation and you won't get a reply. So go to our website and everything is there. It's very easy. You can even use it for free for classroom use. There's no payment for that. There's just a little bit of paperwork. But for personal use, there's no paperwork. It's just filling out one web form. Okay, so here's a problem we are going to solve. So this is a primal problem that MOSEK can solve. So we are minimizing a linear function, so x are scalar variables. And then we have a term there with brackets, and that is a semi-definite term, so to speak, because the x bar variables are symmetric matrix variables. And I can't...
There's a stick on the table. Yeah.
Oh yeah, that's what I need. So this is a symmetric matrix. It has to be positive semi-definite. And so this is simply the inner product between a symmetric matrix and then my variable matrix. So you just x11 times c11, and then you do this, and then you just add it together. So it's just an inner product by a scalarized version. Okay? So this is a linear expression, and we have a linear expression here too, and we can impose bounds on that. And we have bounds on the scalar variables. The scalar variables are allowed to be in a cone. And I'll say a little bit more about that. So down here I have summarized what I mean by this type of inner product. And that's a scalar. And this represents a convex cone. Yeah. Okay. And here's an example of the type of cones that we allow. So we allow some of the scalar variables to be in a quadratic cone. So this is a quadratic cone, and some of the other variables in another quadratic cone. So you can have a bunch of smaller quadratic cones, and they may also be of the rotated variant. And any scalar variables currently can only be member of one subcone, but we can always work around that by introducing additional constraints and variables. Okay. So in MOSEK we employ a primal formulation, and so you can see the semi-definite addition that we added is basically an extension of the linear and the conic quadratic case. So we can just remove this part, and then we are back to the linear case or the conic quadratic case. So that was very convenient when we added the semi-definite stuff. We didn't want to break the compatibility with the older version. Okay. Yes. We don't, in MOSEK, you are not able to formulate LMIs directly. So you have to introduce them by adding the constraints and then adding some slack variable, and then you should say that the slack variable has to be positive semi-definite. Or if you really have a problem with only LMIs, then you should probably dualize it and then solve the dual form, and then you get back to a semi-definite problem on the form that we can solve. Okay. Normally, the data matrices C bar j and aij are sparse, and we exploit that in MOSEK. Okay. These could potentially be completely dense but low rank, and that could be exploited, but currently there's no way of telling MOSEK that these matrices are low rank matrices, dense low rank matrices. But we may add that at a later date if that turns out to be important in practice. Okay. So now I will talk about how you can use a semi-definite optimizer in MOSEK. So we have essentially a number of different interfaces. One is what we call the optimizer API. So that is an interface that brings you quite close to the optimizer implemented in MOSEK. And that interface is matrix orientated. So that means you are essentially inputting the matrices in the original primal formulation directly. It's flexible, it's very efficient, and I know there was made a link to MOSEK from Yalmib, and he says that MOSEK for small problems is way more efficient than Zedumi if you solve a bunch of small problems, because there the setup time is a dominating part, and that turns out to be much faster for MOSEK than a lot of the other SDP solvers available. So we have a very efficient interface. So if the setup time is important for you, then this works. Okay, so efficiency in this interface is more important than ease of use. It's available in C, Java, .NET, and Python. And we have also made sort of the same interface available in R and MATLAB, and that is in fact what Yalmib is using. Then we have a new interface which is called Fusion, and that interface is not matrix orientated, but it rather deals directly with variables and constraints, and that gives you a good compromise between efficiency and ease of use, and I will show you how that interface works. And it's available for Java, MATLAB, .NET, and Python. Okay. Then there are both CVX and Yalmib have made interfaces to MOSEK, so you can also use a semi-definite optimizer on MOSEK from CVX and Yalmib if that's what you like. Okay, let's start by showing how can you call a semi-definite optimizer from MATLAB. And here's a small example. So you have a few scalar variables. You have one 3 by 3 semi-definite variable. You have one quadratic cone constraint, and then you have some terms here with a semi-definite variable. Okay. So, and then you have two equalities. So how do you input that to MOSEK? Well, you have to build a structure, or MATLAB structure, and I call that the problem. And there's of this structure, there's something called C, and that is the objective function for the linear variables. So we had three linear variables, x1, x2, x3, but only one of them appears in the objective, and it has a 1 in front of it. And so that's what you have here. This is a vector where you tell the dimension of your symmetric matrix variable. In this case, we have one symmetric matrix variable of dimension 3. So that's why this is a vector of length 1 and has the element 3. The first element has a value 3. And the next thing we do is that we specify the bar C corresponding to the first semi-definite variable. And the way we do it is that we specify the lower triangular part of this matrix on coordinate form. So first variable, C bar ij in the first position is 2 and so forth, right? So sub j is the index of the semi-definite variable, and k and l is the index into the matrix, and this is the corresponding value. And in a similar fashion, you can specify the elements of the bar A matrix, but here we need 4 indices because this is a constraint, this is a semi-definite variable, and this is the index into the matrix element. So now in semi-definite optimization, you're basically working with matrices of matrices, right? So this is kind of strange. No, not strange, but for the linear case, we only have just a simple matrix. Yes. Then you have to tell something about the cones, if you have some quadratic cones. And here we had one quadratic cone, so this is just a marker telling that we had a quadratic cone. And the variables on the cone was 1, 2, and 3 because x1 was greater than equal the norm of x2, comma x3. So this is it's an area that lists sort of the elements in each cone sequentially. And in this case, this shows where the first cone begins. So in this case, we had one quadratic cone. It starts at position 1 here. So if you had a second cone, for instance, x5, x6, x7, then you would have a comma 2 here, and then you would list the indices there. Here you call the optimizer, and you're telling that you're minimizing, and down here you get out the solution. Okay? So this is sort of, you just specify all the matrices, feed it in, and you optimize, and then you get out the results. Okay. So the advantage of this kind of interface, it's easy to explain, it's quite efficient. The drawbacks are that the problems, in some sense, when you're formulating a problem, you're thinking about constraints and variables, and you may have different variables. But here you sort of have to serialize the problem. And if you suddenly, let's say you remove a constraint, then you have to re-index everything. And so it's kind of nasty. And that's, I guess, why you use CVX or YALMIP, because they make all these things quite a bit easier. So even small problem changes requires error-prone changes to the code. Okay, so two solutions is CVX and Yalman, and they are nice products. But at least they have some disadvantages for people in industries because they are both, at least currently, only MATLAB based. And in industry, like in finance, some people they want to use MATLAB, but they also want to use Python. They want to use MATLAB. They want to use not so frequently .NET. They even sometimes want to use C++ or something else because they have to fit the code that they develop into some usually major company system, and they may not want to use MATLAB. Okay, so at MOSEK we wanted to build an interface that made it easy for people in industry to develop or build models, allowing them to use whatever language they were used to. Okay, so we developed a new interface called Fusion, and the essential idea in Fusion is quite simple. You can minimize a linear function, and then you can define a linear expression over your variables, and then tell that that is a member of a cone K. Okay. So the way you should think about it is that these variables here could be either scalar variables or they could be symmetric matrix variables. Okay. And this set is always a convex set, and that is we won't allow arbitrary convex sets, but we will only allow the convex set that are sort of maybe a quadratic cone, maybe a box, or the positive orthant, or the matrix of or the cone of positive semi-definite matrices. So all you do in Fusion is that you define these linear expressions here, and then you tell it in which cone it has to lie in. Okay? And you will see that later it's possible to have several variables, so not just one x variables. So you don't have to serialize things and just make one big giant matrix as you have to do in Sejumi. Okay? Let's try and give an example. The previous speaker also mentioned this example. That is the nearest correlation matrix. So the problem is that you have a matrix, and this matrix may not be positive semi-definite, but you want to find the matrix that is closest to this fixed matrix that is positive semi-definite. So for instance, think about that you have an estimate for the covariance matrix, and sometimes in finance they sort of generate the covariance matrix by, they may start out with something that is positive semi-definite, but then they modify things arbitrarily in the matrix. But then they have no way of making sure that it's positive semi-definite, right? Okay, so what we do is that we minimize the Frobenius law of our positive semi-definite variable minus the fixed matrix, and then we have some kind of normalization there. Okay, and we can give that a conic formulation by introducing a additional scalar variable t, and then we say t is greater than equal the 2 norm of this. And what we write here by S-weight, we essentially means we vectorize this, and then we take the lower triangular part, and then we set that equal to z. Okay? And then we say the diagonal of x has to be equal to e, that is the vector of all 1. Okay. So it's fairly easy to formulate this on paper, but it's quite cumbersome to formulate this in standard form as the one MOSEK, the format MOSEK used on the previous slide, or Sejumi or SDPA format or something. So here, we have this interface called Fusion, And here I will show you how to implement the nearest correlation problem in Python Fusion. And so if we forget about this and go down here, then this is a Python function. We define A is our matrix, and a matrix in Python is basically a list of vectors. Okay. So I start by creating a model object and give it a name. Then I take the length of A. So remember, the matrix is encoded as a list of vectors. So n is essentially the dimension of the matrix. Then I define a variable x, and I call my variable x, and it has to be in the positive semi-definite cone of dimension n. Okay. The next thing is that I want to encode this constraint. It should be read equality here, right? But I want to encode that constraint, and the way I do it is I create a variable t set. So it's essentially a variable that is the concatenation of t and set, and it has to have this length. And so what I'm saying here is that I'm creating a variable I call t set, and it has to be in a quadratic cone, and the dimension of the quadratic cone is like this. Okay? And then I can say that now, just for notational purpose, that the first element in this variable I call t, and the last elements from 1 and up to the last element in the vector I call set. Okay? Now I want to express this constraint here, and the way I do it is, okay, so I convert this list of vector representation to a dense matrix, and this is sub. So this means this minus this. So sub stands for subtraction. Up here there's an additional helper function, and it gives me sort of the vectorized lower triangular part of this expression here, and then I do a sub again. So I subtract set. So essentially I move set over here, and then it says minus set. And then I say this has to equals 0. So I essentially express this constraint. And down, okay? And then I had to have the normalization constraint, and I do it like this. So I say x dot index I has to be equal to 1. Okay? Down here I tell that the objective should be minimized, and I tell what the objective is, so the linear expression, and here I solve the model. To some extent, I would understand that you don't get too excited about this, because you would like to write things exactly like this or like this, right? But this, in fact, building a model in Fusion compared to building a model using the interface I showed you previously, then this is way faster and much less error prone. So this is a big step in the direction of making it easy to integrate conic quadratic models or semi-definite models into Python or something like that. Okay. So I've used it myself quite a lot, and it seems to be a very nice interface for building models with structure. And let me see. Okay, so let's summarize about Fusion. So I haven't shown all these details, but essentially this is an interface that makes it easy to add and delete variables, and you don't have to, if you in your model have some variables called x, y, and z, you don't have to concatenate them into one big x variable and keep track of where are they located and all this. You can get much closer to the paper model. It's not a modeling language in the sense that AMPL and GAMS is a modeling language, but it's an easy to use API, and in many cases will work like a modeling language. It's designed for efficiency, so this interface it's much closer to the optimizer than CVX and YALMIP. Okay, so CVX and YALMIP are more powerful in what they can express and allow flexibility, but this is much more efficient than they are. At least that's our claim. It's available for Java, MATLAB.NET, and Python. And if you have implemented, let's say, something in Python, then the same thing can be implemented in Java quite easily. So the models look the same in all languages. So if you, for instance, many people like to implement things in stuff for convenience, implementing things in Python for convenience, but Python is not the fastest language on earth, then they may want to move to Java for the final code, and they can do that easily. Okay, I think I have a few minutes left, right?
Yes, so 5 minutes.
Yeah. So I will skip almost all details of implementation. In fact, I'll skip all of them. So I will show a little bit of benchmarks. So I did some computation on a Windows server, and this is something about the CPU. We used 2 threads, and the test problems is taken from some problems Hans Mittelmann makes available. We skipped some of the smallest, and we skipped some of the largest with respect to running time. And here are the number of constraints, the number of quadratic cones. So there's no quadratic cones in these problems. This is the number of scalar variables, and this is the number of matrix variables. So here they only have one big semi-definite variable. Here they had a lot of probably smaller semi-definite variables. Okay? So these are sort of small to medium-sized problems, I think. Here's the primal objective value. This is the number of significant figures. We use a primal dual method, so we compute both the primal and dual optimal solution, or the optimal solution. And so this is the number of figures that are identical between the primal and dual objective value. And we are sort of satisfied if this, for a semi-definite problem, gets above 6, or preferably above 8. We can get that in all cases. Here we only got 4 figures of accuracy before we got into numerical problems. This is the number of iterations, and this is the number, this is the time in seconds. Okay? So at least this shows that we are able to solve semi-definite optimization problems, and we get quite decent accuracy for most of the problems. But of course, sometimes it may be time-consuming. And this talk this slide is kind of interesting with respect to a question from the previous talk, because one guy asked, shouldn't you use iterative method, right? The only place where iterative method, so this slide shows the percentage of time spent in pre-solve. I won't tell you what that is. This is the time spent in factorization setup. This is time spent in computing the Schur complement, and this is the time spent in doing the factorization. And so that's what the question goes on. So if you look down here, okay, there are a problem here where 77% was spent in the factorization. Maybe iterative method could help there. But for the majority of the problems, at least of these problems, you don't spend that much time in factorization. And so iterative methods may play a role and be useful. You can find a precondition. But you should remember there's a lot of problems where factorization doesn't matter. In fact, we use the Nestor-Todd search direction, and there you have to do some singular value decompositions in order to compute the step size to the boundary of the cone, and this turns out to be a bit expensive, but it's not parallelized in our current code. Okay? Yeah. So, current status. MOSEK has been extended to handle semi-definite problems. We have a new modeling tool called Fusion. We can solve large semi-definite problems, and I write the usual restrictions apply, and by that I mean you have to store your matrix variable, right? And so if you have a matrix variable of 10,000 by 10,000, you need a lot of memory, and that's before we start doing anything, right? So preferably it's better to have a bunch of small matrix variables, then probably MOSEK is a good choice. If you have a matrix variable of 100,000 by 100,000, there's no way we're going to help you. Future work, there's we have a one-star technique, in fact, that seems to work quite well for interior point methods for the linear case and the second-order cone case. So we are working on adding that, and that can be generalized to the semi-definite case. On some, we can improve the parallelization of the code quite a bit, and we can exploit this new Intel Phi 1 teraflop card, maybe. It has some interesting, it's very good at doing dense matrix multiplications and things like that, and we may be able to exploit that to speed up computation of semi-definite problems. The stability of MOSEK can be improved, and there's a technique suggested by Jostyr a long time ago, and that is something we want to add, and our preliminary results shows that this can improve the stability quite a lot, so we probably do these accuracy results quite a bit better when we have that implemented. You also have to solve this Newton equations system. I haven't talked too much about that, but using kind of iterative method to improve the numerical stability and not the speed is also something that's interesting. We can exploit low-rank structure and see bar C and bar A. And this tool, Fusion, we don't have a C++ variant at the moment, but have been asked about it. But the main problem is that you need to have some kind of automatic garbage collection in order for it to be useful. Otherwise, it will be too hard. Because when you use something like Fusion, you create a lot of intermediate objects, and if they are not garbage collected automatically, it's kind of a pain. Okay, so that was the only reference about this, how to improve numerical stability. So I guess that's all what I want to say for today. The only thing I will say, one tiny thing, is we are very happy if someone has some problems. There was one guy mentioning LMIs earlier. If you want to talk to us, show your problem and help us, you want some help about formulating and telling you about the structure, we are very happy to work with users to try to speed up things and learn from you what kind of problems you want to solve. So just send an email to support@mosek.com and we can take it from there.
Okay, thank you. Very short
Just a very short comment to this iterative methods, because we are talking about it a lot now. But it's not only doesn't help with the speed, as you mentioned, but it's also the question of the memory. That if you use iterative methods, you don't have to store the Newton system, and we are able to solve much larger problems than we would be able to solve with Cholesky, for instance.
But I will argue, if I solve, then if the Cholesky time is small, the matrix I'm factorizing has to be small, right?
Yeah.
Yeah.
We have problems with, let's say, matrix of size 10,000, which is a dense matrix.
Yes.
So it can never be stored as and the Cholesky factor, but we can solve it by the iterative method because we don't have to we don't have to store the matrix and compute the matrix explicitly.
Yeah. That's of course correct.
It's just a comment too.
Yes. But you know, in all the cases where I showed that the factorization time was quite small, you don't have that issue. You don't have that issue. I fully agree that there are problems where that's an issue, an iterative method can be useful.
Maybe we can leave this for a panel discussion because we are a little bit late. Thank you again.